Good afternoon, folks. Happy Monday. It's been a while since we've done a problem, and I wanted to add a fun and compelling practice problem to our playlist here because, if we keep doing the blocks and pulley and string stuff, we're going to get bored with all the mundane crap that keeps getting thrown at us. So let's kick things up a notch. Let's inject a little adventure into what we're doing. As you can tell from the subtitle here, this time we're going to Mars. So let's get into the problem description. This time, we're part of a design team for the future exploration of the planet Mars. And we're given the acceleration due to gravity on the planet Mars being equal to this value. And if you're wondering what this subscript symbol means, it's just the astronomical symbol for the planet Mars. So really, we're just given the magnitude of the acceleration due to gravity on the planet Mars being this value. And we have this explorer, this this daredevil explorer, mind you, who wants to step out of a moving survey vehicle. And we're told that the vehicle is traveling horizontally at this constant value, which is 1,200 meters above the surface. And once this person steps out of this traveling vehicle on top of a cliff, they're going to free fall for 20 seconds. And then after that 20 seconds elapses, they engage this portable advanced propulsion system, which is quite a mouthful. And I don't want to say that every time. So in short, we're going to refer to that as PAPS. And what is the PAPS thing going to do? Well, that is going to exert a constant force that will decrease the explorer's speed to 0 in the x direction and the y direction the instant they touch the surface. And we're given the total mass of the explorer and all the stuff that they're wearing and all the PAPS and everything, and it's this nice, neat, and round 150 kilogram value. And so what's our responsibility? Well, we have to find the horizontal and vertical components of this PAPS force to 2 significant figures, and then we also have to figure out how long that PAPS has to be turned on for to 3 significant figures. And thankfully we get to ignore air resistance. But before proceeding to calculate anything, I'd like to take a moment to define what this PAPS is. Because let's be real here, unless you're a person who's already experienced in engineering or physics or whatever, this phrase here is probably gibberish to you. And that is completely fair. So let's take a look at some really cool images I found off of Google when trying to get like a better picture of this. And so here is one of 2 pictures here, some digital images by an artist named Albin Merle off of artstation.com that basically shows us, kind of vaguely at least, that the PAPS thing that we're talking about can kind of be envisioned as like a space jetpack that an astronaut would wear. Okay, this is going to allow our explorer to safely cliff jump on the surface and not die the moment they hit the ground. Okay, so now that we can kind of picture what this is and what it's trying to do, let's draw our picture. We'll start off with the Martian surface. We have our cliff. It's 1,200 meters above the surface, or above ground level, whatever. And what's going on there? Well, our person is in the vehicle. They are moving at that constant value, that 33 meters per second. And then what? They get to the edge, and they step out, and free fall, and fall, and fall for 20 seconds. And then what? Well, then they engage the PAPS. They turn that on. So that's now fully engaged. And there's a force that is slowing them down in the x direction and the y direction so that once they hit the surface, they are completely motionless and safe. So that's our picture. And Since there's two kinds of motion occurring during the jump, the free fall in the beginning and the PAPS motion at the end, it would be really helpful to kind of mark where the transition occurs and then maybe break things up into stages. Or at least that's kind of how I did things, because it feels like a compound problem or a compound motion problem where the transition occurs right here when they go from free fall to PAPS, and then we can kind of break this picture up where stage 1 is the free fall stage within the first 20 seconds off here to the left, and then stage 2 is the PAPS motion for however much time is remaining. We don't know. We actually have to solve for that. So using this concept of stages, here's our plan. I'm going to use projectile motion for the first 20 seconds of this free fall, because it's basically like the Explorer is like being launched off of this cliff at a 0-degree angle. And after the fall, the 20 seconds, whatever motion this person has at the end of stage 1, that becomes the beginning motion for stage 2. So since we can't directly jump into like solving for everything in stage 2, we're going to figure out all the motion throughout stage 1 and to the end, and then we'll use that as the beginning stuff for stage 2. So regarding stage 1, here is all of the Explorer's motion at the end of that stage. And this is all purely as a result of the free fall. I'd like to go through each component here, okay? So we can see how we're getting it, and we're all on the same page before we move on to stage 2. Let's start with the acceleration components on the left here in red. For the X component of the acceleration, we don't have anything. There wasn't any acceleration in that direction when the Explorer walked out of the vehicle at the top of the cliff, nor was there any acceleration in the X direction when they were sitting in the car, right? Because it was moving at a constant rate, which implies no acceleration. And so there's no acceleration in the X direction in the beginning or in the middle or at the end. It just stays 0 the whole time for that first 20 seconds. So that's the story regarding that component. For the Y component, we were explicitly given the value of the acceleration due to gravity on Mars. That's that 3.7 value. We just needed to slap a negative on this because in our picture, or at least my picture, as we'll see in the free body diagram, the downward direction is negative, right? So if you're being pulled in the downward direction by the acceleration, it's going to be negative. So that's where that is coming from. The acceleration is kind of covered here. Let's move on to the velocity. It's kind of cool regarding the X component because we kind of get this for free from earlier. They already told us about this, and since there's no X acceleration to change this value, it just stays that way for the entire time, right? They just keep this 33 meters per second X velocity throughout the entire 20 seconds of the trip. The Y component does change, however, right? It gets more and more negative, right? You jump off a cliff, your speed is going to decrease towards the ground, in the negative direction, and that's what's occurring here. So we said that the person was like, it was similar to them being launched off sideways at 0 degrees. So that means there's no initial velocity in the Y direction. And what we're going to do is take our vertical acceleration and multiply that together by the amount of time we're falling to get the vertical velocity at 20 seconds. And so for reference, this is coming from the following kinematic equation. Okay, I start with this kinematic equation. I set everything in the Y direction. Remember that I just said that there was no initial velocity in the Y direction because they got launched off horizontally, essentially, because they walked off that way. So this gets thrown away, and what is remaining is the part here and above that we're multiplying together. And so when we do that, we get what's listed in bold here. So that's it for the velocity. What about the displacement? Well, regarding the horizontal displacement x, I'm going to grab another kinematic equation. It's going to be the position one, and I'm going to set everything regarding the x and the v and the a. All of that is tuned to the x direction. And so there's no initial horizontal displacement that we were told about. So this part can be immediately thrown away. That's equal to 0. Furthermore, we said that there was no acceleration in the x direction the entire time. So that means if you have 1.5 times 0 times t squared, well, the whole thing is going to be equal to 0. So let's just throw that away too. So what's remaining is what's being multiplied together here. And after 20 seconds of free falling, the person is located 660 meters horizontally displaced from the edge of the cliff. And the vertical displacement is going to be a similar story. We have the same equation going on, same kinematic equation, but we're switching the dial from the x direction to the y direction this time. And we do have something that we can cancel out in here. This piece here wants us to multiply an initial vertical velocity times a time. Well, we already mentioned over here that there is no vertical initial velocity when you just walk off a cliff horizontally. So that part gets thrown away in this expression here. And what remains is what we have up here. And what we're left with is the remaining vertical displacement after falling for 20 seconds. So we still have over a third of the fall to go after you fall for 20 seconds straight. So that is pretty wild. That's some good air. So with all the motion at the end of stage 1 figured out, we can now move on to stage 2. And first, let's make a free body diagram. Before, in stage 1, the only force acting on our explorer was their weight. And, this is what it would look like. Hence why I didn't even draw it. It's so trivial. However, in stage 2, that is no longer the case. Now, we have the components of a PAPS force acting vertically as well as horizontally. And the idea is that the vertical PAPS force has to be large enough to cancel out the effects of the weight and produce a positive acceleration to slow that explorer down vertically. And then the horizontal PAPS force is pointing in the negative direction so that it produces a negative horizontal acceleration to slow the explorer down sideways. And here's a representation of what those accelerations are going to look like. Remember, in the sideways direction, the person is already moving at 33 meters per second. So we need to slow them down from a positive velocity down to 0. So that's kind of indicating why this horizontal piece is pointing in the left direction. But this is all the forces in the free body diagram. There is nothing else acting on the explorer. So we are free to move on to summing them accordingly. So I'm going to move our diagram here off to the left and bring F equals ma into the arena. And we'll start with the sum of forces in the x direction like we've done before. So what do we have going on? So we have the force of PAPS in the horizontal direction pointing to the left. So it's going to be negative here. And the resulting acceleration, because of that, is also going to be negative. It's going to be pointing in the left direction. So we don't have F equals ma. We have negative F equals negative ma. And if you are like me, you may not like working with negative signs. So since there's a negative on both sides, let's just switch these to positive. Okay? I don't really like working with negatives. it makes it more confusing. This seems to be a bit more straightforward, in my opinion. So with that correction made, there's really nothing else that we can do in the horizontal direction. So let's move on to the vertical direction next. We have the PAPS force in the vertical direction pointing upwards, so it's positive over here. Weight points down, so negative. And we talked about how this new acceleration during the PAPS force, it has to be this positive value so that they're slowed down to 0 once they touch the ground. So MA in the y direction is positive. However, this is all fine and dandy, but we don't know what these accelerations are. We are in no position to plug stuff in and just solve for these because we can't. We're going to have to resort to an alternate tactic to get these accelerations, which will then allow us to solve for those forces. And, there's a lot of different ways that you can do this. However, I think the most straightforward way is to start with the vertical direction. And so what I'm going to do is I'm going to use kinematics to get the vertical acceleration first. And the kinematic expression I'm going to use to do that is this one. And you may be wondering, how did I know to choose this one? I promise you, it just didn't fall from the sky. We actually know everything in this expression already, whether you're aware of it or not. If we look at the left-hand side, this variable is asking us, what is the final velocity in stage 2 squared? Well, the final velocity in stage 2 is when the explorer touches the ground and they're no longer moving in the y direction. So that's easy enough. That's just 0. And 0 squared is also 0. So, all right, cool. 1 down, a couple more to go. Let's next redefine this delta y in stage 2 so it's a little more clear what we're talking about. And remember, delta y is just saying what's the difference in the displacement in the y direction during stage 2. Well, the final displacement in the y direction during stage 2 is ground level. That's at 0. The initial one in stage 2, well, that's the final value we had in stage 1. That's that 460 meters that we had left over. Additionally, this value, or this variable, pardon me, is talking about the initial velocity in stage 2 squared. Well, the initial velocity in stage 2 is the final velocity of stage 1. So let's plug in some of these values, since we quite clearly know what they are already. And the goal is to algebraically solve for the acceleration in the y direction during stage 2. And that's what I'm going to do. Notice that in this line here, I've multiplied this coefficient of 2 by this negative 460 part here, so that we don't have a difference floating around. And so we have negative 920 meters multiplied by the acceleration that we want. So I'm going to swing this portion of the expression over to the other side, like this, and then divide both sides by 920 meters, which results in the following. And if we did it right, it should be a positive value. And if I take a negative number, I square it, it becomes positive, divided by another positive. That is indeed a positive value. So this is the new acceleration that you feel in the y direction when you turn PAPS on. And why did we want to solve for this? Who cares? Well, we're going to use this to solve for that vertical PAPS force, because remember, our expression from the sum of forces in the y direction was this. And we know what the weight is, but we previously did not know what was on the right-hand side. Well, since we know it, we can solve for it now. Let's take the weight and swing it over to the other side to isolate the PAPS force in the vertical direction. And we can also rewrite the weight to be mg. But remember, it's not regular mg like on Earth. It's mg on Mars. Okay, so hence the inclusion of this symbol here. And we have a mass in both of these terms. So if we want to be fancy, we can factor that out. And notice that we're taking the explorer's mass and all their stuff multiplied by the sum of the accelerations that they are experiencing. And it's going to be a positive value, of course. On my calculator, I get the following, and remember that we needed to report this to two significant figures. So we're going to have 1.4, okay, our decimal point will be right here, and we'll be raising it to the following exponent in scientific notation. So 1, 2, 3. So hence, if I rewrite this appropriately, we get 1.4 times 10 to the third newtons. And that is the answer for our vertical PAPS force. Okay? One force component down, one to go along with the time. Okay? So 1 out of 3 things done. Cool. What should we do next? You might be thinking maybe the horizontal PAPS force. Well, I see where you might be going with that. However, we're going to need a time. And unless we get a time first, we're going to get a little bit stuck. So, with the vertical PAPS force complete, let's maybe use the information that we have here to solve for the time to fall the remaining vertical distance with PAPS turned on. Here's what I mean. I'm starting with this expression here. Why? Because I want to solve for a time, and all these other things I know. I just solved for this acceleration value. I know what that is. I know what the final velocity of stage 2 is going to be, and I know what the initial value of stage 2 is. So let's move things over algebraically and solve for the time like this, and then we can plug in all the values that we know. Okay? Remember we said the velocity in the y direction at the end of stage 2, 0. The beginning velocity in stage 2 is the ending velocity in stage 1, so the negative 74 meters per second value. And then for the acceleration in the y direction in stage 2, we're just using what we previously solved for in the last slide. And what do you get? You get this value. And here is a very helpful reminder. This may represent the amount of time it takes to slow down in the y direction, but we need it to be the same as the time to slow down in the x direction. If you don't slow down in the same amount of time in both directions, you're either going to hit the ground and then move forward or backward or something, or you're going to hit the ground and then PAPS is going to try to like bring you, down even more or something, right? We don't want that occurring. We don't want the person to die or experience some kind of like horrific accident. We want them to cliff jump, and the moment they hit the ground, it's 0 in the x, 0 in the y for velocity. So that means it has to slow down in the same amount of time in both directions. So we're kind of getting this answer for free. This is the total amount of time that the PAPS has to be turned on, because it takes PAPS the same amount of time to slow down in either direction. So hopefully that's not too confusing, but that is the time that we're going to use to solve for our remaining component that we need. And so we'll do this approach in the same way that we did in the vertical direction, where we solve for the acceleration first, and then we use that to get the force. So here's the expression I'm going to use. It's the same one that we just had, but I'm working in the x direction now. And what am I going to do? I want to solve for the horizontal acceleration, this piece here, a sub x2. And so I'm going to algebraically manipulate it and isolate that variable. And I know the numerator, and I just figured out what the time was. And so that's going in the denominator. So I know what this is now. Looks like I switched the direction here. Sorry about that. Hopefully that's not too confusing. I can plug all of this stuff in, and what should I be getting? I should be getting a negative value based on the picture that we drew in the free body diagram. And in fact, if you take 0, subtract a positive number, and then divide it by another positive number, you indeed get a negative acceleration. And so, since we have the key to what we want to get at now, let's plug in our expression. So we take FPAPS multiplied by this, which is just this expression, and I get the following on my calculator. If we truncate this to 2 significant figures, my decimal point is going to be located right here, and I'll have to multiply this by scientific notation, and my exponent on the 10 is going to be 1, 2. So looks like we have negative 4.0 times 10 to the 2 newtons, representing our horizontal PAPS force. And so that is our last one. Let's kind of bring these all together on the solution card. So we have our horizontal PAPS force, which pointed to the left, being represented by this negative value. We have our vertical PAPS force pointing in the plus y direction, being represented by this positive value. And here was the amount of time that the PAPS is going to be engaged. Okay, it's the same amount of time it takes to slow the Explorer down in the y direction as it does the x direction. And now we have successfully designed a cliff jump mechanism for our Martian Explorer. It's pretty sweet, huh? I hope you enjoyed it. Take care, everyone.